Welcome to Understand Chemistry. I am Dr. Bilal and this is the second video in our series on copolymers. In the previous video, I discussed the types of copolymer based on their structure and derived the Mayo-Lewis equation. In this video, I will discuss in detail all types of copolymerization. There was a small omission in that derivation. Before the brackets, the terms m1 over m2 refers to concentrations and should be enclosed in square brackets. I have already clarified this in the video description. So let's get started. Let's begin with the Mayo-Lewis equation. It can also be expressed in terms of the mole fraction of the monomers. If lowercase f1 denotes the mole fraction of monomer m1 in the feed or mixture, it can be written as f1 is equal to m1 over m1 plus m2. Similarly, for the monomer m2, we can write f2 is equal to m2 over m1 plus m2. In the same way, if uppercase F1 represents the mole fraction of monomer M1 in the resulting polymer, we write F1 is equal to small case m1 over m1 plus m2, and similarly F2 is equal to m2 over m1 plus m2. Using these mole fraction expression, we can isolate the value of m1 and m2 in both the feed and the polymer. Substituting these in the Mayo-Lewis equation and simplifying, we arrive the following form. This is the Mayo-Lewis equation expressed in terms of mole fractions. Now let us explore different types of copolymerization in detail. Let us now look at ideal copolymerization, where the product of reactivity ratios, meaning R1 into R2 is equal to 1. It defines a special case. In this scenario, the propagating radical M1 and M2 propagating radical show same preference for both type of monomer. The result is a truly random incorporation of monomers into the growing polymer chain. Mathematically, we define the reactivity ratios as R1 is equal to K1 over K12 and R2 is equal to K22 over K21. Here K1, K11 and K22 represent self-propagation rate constant, means the growing chain radical M1 adds monomer M1 and M2 radical adds M2 monomer. For ideal copolymerization, the product of these ratios equal 1. In other words, the reactivity of monomer M2 is the reciprocal of that of M1. Substituting the value of R2 is equal to 1 over R1 into the Mayo-Lewis equation and simplifying, we obtain the rate of change of the concentration of monomer M1 with respect to monomer M2 is equal to the product of reactivity ratio R1 and the concentration of M1 divided by the concentration of M2. Similarly, placing R2 is equal to 1 over R1 into the mole fraction form of Mayo-Lewis equation and simplifying, we get the ratio of monomer 1 in the copolymer to the monomer 2 in the copolymer is equal to the product of the reactivity ratio R1 and the feed fraction of monomer 1 divided by the feed fraction of monomer 2. To express this equation solely in terms of the mole fraction of monomer 1, we use the fact that the sum of mole fraction in a system is equal to 1. So substituting F2 into the previous equation and simplifying, we arrive at this equation. Let's compare two types of copolymerization, ideal and statistical. In the ideal case, where both reactivity ratios R1 and R2 equals 1, the two monomers show equal reactivity. This means the copolymer composition exactly matches the monomer feed composition. The placement of monomer along the chain is truly random, what we call Bernoullian distribution. This type of copolymer is also referred to as azeotropic copolymer because there is no composition drift during copolymerization. In contrast, in statistical copolymerization, the reactivity ratios are unequal. For example, R1 is less than 1 and R2 is greater than 1 or vice versa. Here, one monomer is more reactive than the other. As a result, the copolymer contains a large proportion of the more reactive monomer. The incorporation of monomer is governed by their reactivity, not by feed composition alone. This leads to composition drift and non-azeotropic behavior. The composition drift means the change in copolymer composition during the course of polymerization, even when the monomer feed composition remains constant. To better understand this, let's look at the plot. On the x-axis, we have the mole fraction of monomer M1 in the feed, that is small case f1. On the y-axis, we have the mole fraction of M1 in the resulting copolymer, that is capital F1. The curves show how F1 changes with the F1, small f1 for different values of reactivity ratios R1 and R2. For each curve, the reactivity of monomer 1, R1 is written in red. The value of R2 is chosen so that the product R1 R2 is equal to 1 in all cases. Let us first discuss the diagonal line. It represents the case in which both R1 and R2 are equal to 1. This is called the azeotropic line or the ideal copolymerization line. Here both monomers have equal reactivity, so the copolymer composition exactly matches the feed composition. That means capital F1 is equal to small f1 at every point. To clarify, if we choose 3 points on the curve, for example f1 is equal to 0.61, capital F1 is equal to 0.4 and 0.2, we find that the corresponding small f1 values are also 0.6, 0.4 and 0.2 respectively. For this case, we have a random distribution of monomer along the chain, also called a Bernoullian distribution. The copolymers formed on this line are referred to as a truly random copolymer, as monomers are placed randomly along the chain. There is no composition drift during copolymerization. But when R1 and R2 are not equal, things change. One monomer becomes more reactive than the other. It gets incorporated more quickly and the copolymer ends up richer in that monomer. This is called statistical copolymerization or non-azeotropic behavior. The curve deviates from the diagonal, showing how the copolymer composition shifts away from the feed. To better understand this, consider curve A, for which R1 is equal to 10 and R2 is equal to 0.1. This is an extreme case when there exists a large difference in the reactivity. The product R1 and R2 is equal to 1, which is typical for ideal or random copolymerization. However, since monomer 1 is much more reactive than the monomer 2, it will appear more frequent in the copolymer chain. There may still be a statistical pattern in the monomer distribution, but the resulting copolymer will be classified as a statistical rather than truly random. Let's consider another curve for further clarity. In case of curve C, R1 is equal to 2 and R2 is equal to 0.5. So again R1 into R2 is equal to 1. Here the difference in the reactivity is not too large, but monomer M1 will still appear more than monomer 2 in the copolymer composition. This behavior is sometimes referred to as moderately ideal, since the copolymer will be more random than the one discussed before. Now let us take another example where monomer 2 is more reactive. Consider curve E, for which R1 is equal to 0.5 and R2 is equal to 2. The behavior is also moderately ideal, but the resulting copolymer will be richer in monomer 2 compared to monomer 1 due to its high reactivity. Now let us explore another special case in copolymerization, the alternating copolymerization. where the product has a perfectly alternating structure regardless of the monomer feed composition. This behavior occurs when the product of the reactivity ratio R1 into R2 is 0. That means neither monomer prefers to add itself. Instead, each propagating species exclusively add the other monomer. So M1 growing radical adds only M2, and M2 growing radical adds only M1. This leads to a strictly alternating sequence in the polymer chain. To understand this mathematically, we start with the general copolymer composition equation. Under alternating condition, where the R1 R2 is equal to 0, in addition to this, for extreme case, we consider when R1 and R2 are equal to 0. The expression simplifies significantly. The ratio of monomer consumption rate dm1 over dm2 becomes 1, meaning both monomer are consumed at equal rates. In terms of mole fraction, we substitute same condition in the mole fraction form of copolymerization equation. That on simplification gives F1 is equal to 0.5. This confirms that copolymer has an alternating structure with equal incorporation of both monomers, regardless of the initial feed composition. There are some situations where alternating behavior occurs, but the monomers are not arranged in a perfectly alternating manner. Some textbooks refer to this behavior as moderately alternating. In this context, consider case 1, a condition where the product R1 R2 is very small and approaches 0, while both R1 and R2 are much less than 1. In another case, the product R1 into R2 is equal to 0, with R1 is equal to 0 and R2 also much smaller than 1. In both cases, the resulting copolymer is not perfectly alternating. Instead, there is some deviation from ideal alternation. The behavior of most comonomers system lies between the two extremes of ideal and alternating copolymerization. As the product R1 to R2 decreases from 1 towards 0, there is an increasing tendency toward alternation. Perfect alternation occurs when both R1 and R2 are 0. The tendency toward alternation from ideal behavior increases as R1 and R2 become progressively less than unity. To better understand this, let's look at the plot. In this plot, the value of R1 varies from 2 to 0, whereas the value of R2 is fixed at 0.5 for every curve. Consequently, the product R1 into R2 also varies from 1 to 0. We already know that R1 into R2 is equal to 0 corresponds to ideal behavior, and R1 into R2 is equal to 0 corresponds to alternating behavior. These are two extreme conditions. In this plot, as the value of R1 decreases from 2 to 0, the product R1 into R2 approaches 0. We can say that we move from ideal to moderately alternating and finally to perfectly alternating behavior. For further explanation, let us consider curve A, for which R1 is equal to 2 and R2 is equal to 0.5. The product R1 into R2 is equal to 1, so this represents ideal behavior, just as we observed in the previous plot. Now, let us move toward lower curve B, for which R1 is equal to 1 and R2 is equal to 0.5. The product R1 and R2 is equal to 0.5. In this case, we are deviating from ideal behavior and copolymer will tend to show some alternation behavior. Further, if we consider curve E, where R1 is equal to 0.1 and R2 is 0.5, the product R1 into R2 will be equal to 0.05 or roughly 0. So this copolymer will show a high tendency toward alternation. This plot also illustrates an interesting characteristic of copolymerization with a tendency toward alternation. For values of R1 and R2 both less than unity, the curve intersects the diagonal line where capital F1 is equal to small f1. At this intersection or crossover point, the copolymer and the feed composition are the same. Such copolymerization are termed azeotropic copolymerization. Let's find the relationship for azeotropic copolymerization composition. As we know, an azeotropic composition is a special point where the concentration of a monomer in the feed is exactly equal to the concentration in the resulting copolymer. In other words, the ratio of monomer 1 to monomer 2 in the mixture matches the ratio in the polymer chain. To find this point, we start with the general copolymer composition equation, which includes both reactivity ratios and monomer concentrations. Through a series of simplification steps, we arrive at the equation that describes the azeotropic point. This equation shows that the azeotropic composition occurs when the ratio of monomer concentration, that is M1 over M2, equals R2 minus 1 over R1 minus 1. This expression tells us that the azeotropic point depends entirely on the reactivity ratios of the two monomers. Let us now find the azeotropic condition in terms of mole fraction. At the azeotropic point, the mole fraction of monomer in the feed is equal to the mole fraction of monomer in the copolymer. Mathematically, we can write the ratio F1 over F2 is equal to the ratio small f1 over small f2. Substituting this condition into the mole fraction form of the Mayo-Lewis equation and simplifying through several steps, we arrive at this expression. F1 is equal to R2 minus 1 whole divided by R1 plus R2 minus 2. So if we know the reactivity ratio of the monomers, we can determine the azeotropic copolymerization composition point. Let us look at the block copolymerization, a process where long segments of different monomers are linked together in blocks. This behavior is typically expressed when both reactivity ratio R1 and R2 are greater than 1. That means each monomer prefers to add more of its own kind, leading to homopropagation. However, for true block copolymerization to occur, the product R1-R2 should also be greater than 1. This balance is rare in conventional free radical polymerization. In practice, we often see that each growing chain favors its own monomer, and the crossover reaction, where one monomer starts adding the other, is slow and inefficient. As a result, instead of forming a chemically linked block copolymer, we ended up with a physical blend of two separate homopolymers. So then, how do we actually synthesize block copolymers? Actually, we use control or living polymerization techniques to synthesize block copolymers. These techniques include ATRP, atom transfer radical polymerization, nitroxide mediated polymerization, reversible addition fragmentation chain transfer, and anionic polymerization. These methods allow us to pause and restart chain, enabling precise control over block formation. I hope the concept of copolymerization is now clear. Thanks for watching.